So, dear participants, today welcome to the day 6, session 11, and one of the sessions I know you are looking forward to. Today's session will be taken by Shailesh sir, and the topic is disaster resistant construction practices. And I'm glad to welcome sir, who was the executive director of BMTPC and the body under the Ministry of Housing and Urban Affairs, Government of India in Delhi. So, sir is a distinguished civil engineer specializing in earthquake engineering, disaster mitigations, sustainable construction materials, affordable housing, and also he previously served as scientist at the CBRI Roorkee. Sir holds the PhD degree in 2001 from IIT Roorkee and Master of Science in BITS Pilani and MTech Structural Engineering from IIC Bangalore. Sir is the BTech in Civil Engineering. He's the silver medalist and sir was involved in establishing the building dynamics laboratory at CBRI Roorkee, which provides the science and technology backup in the area of disaster mitigations. Also, sir was leading major R&D projects, international and national importance in the domain of the earthquake resistant structures, health monitoring of the important structures, seismic vulnerability of buildings, repair and rehabilitation of structures, and many more. So, sir has also published lecture notes for the course in the form of book entitled Earthquake Designer Manual and for Practicing Engineers in December 2004. Sir was invited and felicitated as a faculty member to deliver keynote lectures in the domain of earthquake resistant design and construction at various professional level, national and international conferences, short-term courses, invited lectures, training programs, and many more. SAR has also instrumental in promoting innovative, cost-effective, eco-friendly, and disaster-resilient building materials and technologies, including that initiative under the Pradhan Mantri Awas Yojana, Urban and the Global Housing Technology Challenge India. His work bridge research with the policy enhancing the seismic safety of standards, affordable housing in multi-hazards prone India. Sarah has authored numerous publication guidelines on seismic safety, served as a visiting faculty in institution like SPA, which we know School of Planning and Architecture, New Delhi. His work has significantly influenced national standards and disaster mitigation policies in India. So we are truly honored, sir, to welcome
Thank you,
you
sir.
and
Thank
sparing
you.
your time with us, sir, and would like to express a sincere gratitude, sir, for your
Thank you.
precious time. In
Thank you.
addition, sir, I should say that also we know, sir, that you played an instrumental role for developing the earthquake testing at Dynamics Laboratory at MNIT Jaipur. And personally, I want to say to all my participants that I had contacted sir many times before, and in return, always sir gives the encouraging reply. Always, thank you, sir. Like
Thank
it
you.
is, we are lucky that we have a
Mhm.
guide like you. We always
Thank
shows
you.
the directions, and I never heard no from him. Always he gives the encouraging reply, and also it actually boosts our motivations and everything.
Thank
Thank
you.
you, sir, for always be
Thank
there
you.
with us.
Thank you. Thank you for your kind words, Sushanta. Um, can I share my screen?
Yes, sir, please.
Okay. So you have to allow me.
Yeah. Good.
Yeah.
One minute, sir.
Okay.
Oh, good. Yes, sir, it is done. Please.
Okay. So I'm just sharing my screen. Yeah. WebEx is requested to bypass the system. Okay. Are you able to see? Are you able to see, Professor Sushanta?
Yes, sir. Yes,
Yeah.
sir. Your screen
Is
is
changing
visible.
also? Is changing also?
Yes,
Slides are
yes.
changing? Okay. Okay. Thank you.
Yeah, it's
Thank you.
changing, sir.
Okay. Okay. Thank you. So at
Sir,
the outset,
before
yeah.
you go ahead, one of the coordinators of the FDP, Robin sir, is also there. Robin
Okay.
sir? Robin sir? Maybe he's facing internet issue. Sir, please go ahead, sir. Sorry for the
Okay.
interruption.
Okay.
Yeah. Your screen is
Not an
visible.
issue.
Yeah.
Yeah. So not an issue. At the outset, let me thank Professor Susanta for giving my introduction to all of you. That's very kind and sweet of you, Sushanta, and speaking such a nice words about me. Thank you very much. And I also thank NIT as well as Sushanta and his initiatives with regard to disaster resistant design and construction practices, and also imparting training, education, and spreading awareness about about various disaster resistant construction and the other things. So I will be giving you in general. I'll be taking you through what is disaster resistant construction practices and design. I would also be touching upon, since all of you are faculty members, that what are the changes have been incorporated in very recently published Earthquake Code 1893. That also I'll be touching upon, and then a little bit on retrofitting and repair. Also, I'll be covering, and if time permits, then I'll talk about disaster mitigation management. It's a very exhaustive lecture, which I have prepared for all of you. So, I worked in CBRI, Central Building Research Institute, where I also, developed a testing facility for testing lateral resistance of, whole buildings and building components. And also, after joining Ministry of Housing and Urban Affairs, we have been promoting through Pradhan Mantri Awas Yojana, which is one of the largest affordable housing program being undertaken by Government of India in 2015, where we are going, in different states, and not only imparting training, but also educating the engineers, architects, and artisans with regard to disaster resistant construction practices. Okay, and so let me just first give you the brief. You all know that India, we must understand that India is prone or vulnerable or susceptible to various hazards, various natural hazards, whether it is earthquake, cyclone, landslides, and nowadays these things are being aggravated by extreme events such as rainfall, extreme heat, and thunderstorm is something new phenomena because of heating up of our planet Earth. Thunderstorm is something which is also very lethal nowadays. So all of you, this slide just shows you that these are events, natural hazard events which converted into disasters, and all of them could have been prevented if we would have prepared ourselves better. Whether it is 2001 Bhuj earthquake, cyclones, all of you know, thanks to the early warning system installed nowadays, we have less deaths or less live losses and property losses during the cyclones. Floods, all of you know, nowadays we also encounter flash floods, landslides. Every year we have landslides. 2004 tsunami, nobody can forget, leaving a trail of destruction everywhere. So all these disasters could have been prevented if we would have prepared ourselves better. Okay, then why these things are happening in our country? I have few slides for you, that every now and then, when we compare the similar event happening anywhere else in the world, in Europe or in America or in Japan, the losses of life and property are less as compared to our country. So few slides for that. All of you know we are increasing urbanization, and if I have to give you figure, last census was conducted in 2011. That time 31% India was urbanized, and by 2050, 50% of our population will live in urban areas. That means around 815 million people, that is 81.5 crore people, will live in urban areas. So we are rapidly urbanizing, so we have to take care of that whatever built environment we develop, that has to be multi-hazard resistant. Secondly, all of you know cities, because of land scarcity and other pressures, habitat is being expanded to vulnerable areas such as floodplains. We have marshy lands and whole lot of other things where we have development taking place. Then India, again, as you know, the population density, if we compare with the globally, India population density is very high. That also sometimes lead to higher losses of life and property. Vulnerable construction, all of us know that most of the time, whenever any earthquake strikes or any other event takes place, these non-engineered constructions face the brunt of that, shock, or that earthquake, or any other natural hazard. So that we have, over the years, we have lost the traditional building skills, and what is needed nowadays is to, keep in mind those those vernacular constructions, local material and local artisan skills, and the kind of knowledge we have today. So there should be synergy between the knowledge which we have now and the vulnerable constructions yeah, and the traditional or vernacular construction we used to have. If there is a synergy between these two, we can create a sustainable, safe structure. Particularly with regard to earthquakes, we are, sometimes we do not bother about earthquake because the return period of earthquake is quite high. So sometimes we feel that the earthquake will not come in our lifetime. So why to, incorporate earthquake resisting measures into the new construction? So ignorance, apathy, believing that it will not happen here, and because of long time gap between events, there is that can also be attributed to higher losses of life and property. Non-engineered construction, as I told you earlier, most of despite of having good standards, good Indian standards, every now and then we find that whether it was Latur, whether it is Jabalpur, whether it is Uttarkashi, in all these earthquakes, non-engineered construction, mud construction, low strength masonry construction, all of them, stone masonry construction, all of them suffered huge damages, collapses, and leading to loss of life. This also, if you go to any cities, urban areas, in particular, if we talk about metros, you will find that um, uh, residents or users themselves, they keep on adding, keep on altering the structural configuration of their building or their structure where they live, and that sometimes create more problems because these structures become more vulnerable to shocks. Imagine you converting a balcony into a room, or converting a staircase into a storage space. It will make it more vulnerable or susceptible to future shocks. So any alteration and any addition and deletion in the structure, we need to seek advice of experts, particularly structural engineers, and then only we should go for it. Otherwise, because of the space problems and all, everywhere, vertical extension and addition of rooms and other things are being done. That also lead to higher losses of life and property. So this all of you will agree that urbanization, expansion of habitat into unsuitable vulnerable areas, higher population density, ignorance and apathy about the natural hazards, then non-engineered unsafe construction, and all these things are leading to towards higher losses of life. So all these things exist, and what is the scenario? We have very robust. If I have to tell you that we have very robust technical framework, as well as we have Disaster Management Act, we have disaster management policy, we have I will tell you about the Indian standards. If we talk about Indian standards, we have very good exhaustive Indian standards dealing with all kinds of hazards in the country. And also, if you look at any, we have National Disaster Management Authority, NDMA also, and if you look at the Disaster Management Act or Disaster Management Policy, it clearly indicates, says that there should not be any loss of life during earthquake or during any event. So zero tolerance to avoidable loss of life is the motto of all these things. But despite of all these things, we do have a whole lot of life-threatening collapses during the earthquakes and other events. uh, People by and large not adequately, and that is why these kind of programs are being conducted. After 2001 Bhuj earthquake, whole lot of programs were organized, conducted. Whole lot of organizations came out with literatures, explanatory handbooks and all. But India being a vast country, and last mile connectivity is sometimes missing. Sometimes we do train faculty, we do train prospective engineers and architects, but despite of that, artisans is something which need to be trained. So people are not adequately aware of the risk their shelters are exposed to. There is poor availability of knowledge and know-how at end user level as well. Uh, then, implementation of existing laws is not up to the mark. I can give you example. Like Ministry of Housing and Urban Affairs came out with model building bylaws. Okay, MBBL it is called. It can be downloaded from ministry's website, and then all the state governments were asked to incorporate. To develop their building bylaws based on these model building bylaws. And in modern building bylaws after 2001 Bhuj earthquake, our chapter was included, a specific chapter on disaster management, that if your state or the area where you are working is prone to natural hazards, then you need to incorporate design basis report. You need to get the structural integrity, structural stability certificate from the practicing or authorized engineer. But India being federal country, those bylaws, in some places, in some states, those bylaws are being incorporated, but in some states they are not. And even if they are incorporated, their implementation is not up to the mark. Then, as I told you, last mile connectivity, there have been several programs being run by Government of India, but in fact by NDMA, a whole lot of training programs, sensitization programs, whole lot of social media uploads, then manuals, films, and other things are in place. But despite of all those things, there is lack of adequate mechanism and institutions for dissemination of knowledge. So this is the scenario which exists, and we also know that India is committed to sustainable development goals. And if you can see, the SDG 11 clearly indicates that we have to make cities and human settlements inclusive, safe, resilient, and sustainable. So resilient and safety is part and parcel of any development which takes place. And I have also included here the sustainable goal 13. As we cannot take these natural hazards stand alone. Now we have to incorporate climate change or climate mitigation strategies also into account, because climate is very fast changing. The planet Earth is heating up, temperatures are rising, and because of rise in temperature, a whole lot of things are happening. Also, because of pollution and all, greenhouse gas emission, energy use, India is also committed to be Viksit Bharat by 2047, and also we are committed to become net zero country by 2070. So in addition to safety, in addition to disaster resilience, we need to incorporate climate change mitigation strategies. Like we need to have sustainability also need to be taken into account for the built environment. This is just for academic purposes. You can see here, this slide shows you that hazard and the two words I have been speaking to you. One is disaster, hazard, and vulnerability. So hazard is something which we have to live with. India is prone to earthquakes. India is prone to landslides. So this is a hazard, and we have to live with it. But vulnerability, so hazard is there, but if we create structures which are robust, resilient, we can always reduce the risk. Okay, so risk is something which is quantifiable, and risk can always be reduced despite of having high hazard, by creating resilient structures. For example, suppose an earthquake comes in a forest area, there will not be any risk or any loss. But if the same thing comes in a higher where whole vulnerable structures are there, then risk will be high. So risk can always be reduced by creating resilient or robust structures. And also by building capacities, we can always reduce the risk. So hazard, vulnerability, exposure, all these things are interrelated. Hazard is something which we have to live. If you are living in Delhi, it is in zone 5. Suppose you are looking in northeastern area, which is which falls under highest seismic zone, which is seismic zone 5 now. So you have to live with it. Hazard is there, but you can reduce the risk at that place by creating better structures, by reducing the vulnerability, and by enhancing the capacity in terms of the capacity, not in terms of human resource, but also in terms of structures and built environment. Okay, so this is just a mathematical explanation to hazard, vulnerability, exposure, and capacity. So risk will get increased if exposure is high. So if higher population density, or if in densely populated area, if earthquake or any event takes place, then risk will be high. Similarly, if hazard comes in a place where we have all vulnerable structures, then risk will be high. Okay, so this is just to show you these are some policies which are in place by Government of India. Disaster Management Act 2005, National Policy for Disaster Management 2009. Then in 2016, National Disaster Management Plan was published by National Disaster Management Authority, and under that and disaster management plan, all states, all departments, in fact, all academic institutions as well, are mandated to create their own management plan as well, and submit it to NDMA. But still, that is not being done. Also, India is, partly to this international framework. Every 15 years or 10 years, 15 to 20 years, we have a global framework for disaster risk reduction. So right now the Sendai framework for disaster risk reduction is in place, and India is also signatory to that framework. And all these frameworks or all these acts, the major thing is to shift, is a shift from response centric to reactive to proactive. So normally what happens whenever an earthquake or any other disaster strikes, we are a reactive society. So after any event comes, after that we think of repair, rehabilitation, and relief measures are put in place. But we have to replace that reactive measures by proactive. So in the very beginning, we need to ascertain the hazards or our area is exposed to, and according to that we need to prepare ourselves better. So we need to replace reactive, so R by P, and P means proactive, pre-disaster preventive measures. Okay, so all these acts nationally or internationally, the basis is to bring a paradigm shift from reactive to proactive measures. You can see here, so this is paradigm shift. As you can see here, instead of going for what you see in bottom half, response, rehabilitation, reconstruction, you have to prepare yourselves better. You have to put mitigation strategies in place, and so that you can prevent the future disasters. Okay, and so estimation of the risk your area is exposed to is very important, and once you estimate the risk, then you can always mitigate it by putting mitigation strategies in place. Okay, so always remember that instead of bottom portion, we need to have that proactive pre-disaster measures. Okay, this is just a slide to show you what is the global scenario with regard to earthquakes. Global earthquake risk has gone 4 times, in the past century. I will show you some data also with regard to losses and all. By 2030, 37 cities will be over 10 million, will have more than 10 million people, and 24 of them are in less developed countries, and thereby exposing them to greater risk. Total population, all of us know it was 8 billion a few years back. Now it is going to be 9 or 10 billion by 2015. 8 million earthquake related deaths during past 1,000 years. And eh, we India, as I have been telling you, that in Alpine Himalayan belt and Himalayan region is quite susceptible to earthquakes, and so India is sited on Himalaya, and most of these catastrophe have occurred on Himalayan belt and other seismic belt as well. Then more than half of the world's super cities are located in places where future damage is inevitable. This is a global scenario. Although less than 8% of world population live in mega cities with 10 million or more inhabitants, 56% live in cities which are vulnerable. In fact, in our country also, more than 50% area is vulnerable to high seismic risk zone. This is just to show you yearly. You can see here. Earthquakes, some earthquakes keep coming, and this is just a data which is taken from National Institute of Disaster Management. You can see in 2015, for in our country, more than 600 earthquake events. So around 700 earthquake events, occurred, and all these are magnitude 4 and above. In 2023, the earthquakes which took place were around 300. So these are the so India is prone to earthquakes, and these are the events, year-wise breakup of earthquake events within 300 kilometers of India. Then these are from 2000 to 2000. You can see here 1980 to 19. There we have put the events. Drought, earthquake, extreme temperature, flood, landslide, mass movement, dry area, storm, volcanic activity, and wildfire. So if we look at the flood, you see in the last 20 years, and now this recent 20 years, from 2000 to 2020, you can see the flood risk has increased enormously. Events, similarly, earthquake events have increased drastically. Similarly, storm have increased so drastically. So these are the events which have taken place in last 20 years, and these are being compared from 1980 to 2000. And you can see if this was in numbers, and if we have to convert it into percentage, so majority, see, the major percentage of occurrence of disaster is flood in our country, 44%. Then storms, 28%, and earthquakes are only 8%. And that is why earthquakes, and you can see here the events are more, but sometimes we feel it, sometimes we don't feel it. So this is just a breakup in terms of percentage of occurrence for the last 20 years. Okay, then you can see I told you in the beginning that despite of having policy of zero tolerance to earthquakes, the total number of deaths have been more than 700,000 due to earthquakes. Then around 200,000 due to storm, due to extreme temperature, around 150,000, and 100,000 due to the flood, and 42,000 due to drought, landslide, volcanic activity, and mass movement. So I just wanted to, project a picture to you that all these things could have been prevented had we prepared ourselves better. Okay, and this is the geographical layout of tectonic plates, and this is the seismic tectonic plates, and all of you know that India is Indian plate. India is sitting on Indian plate, which is constantly moving behind the Eurasian plate, and because of constant movement of 5 centimeter per year of Indian plate beneath European plate, this Himalayas were evolved, and because of this movement, the entire Indian region is prone to earthquakes, and Himalayas were evolved because of this movement, and as I told you in the beginning also, Himalayan belt, Himalaya is one of the most active seismic belt of the world. So this is the hazard scenario with respect to earthquakes of our country. Okay, and this is Indian situation with regard to earthquakes. We have more than 100, 140 billion people, 1.4 billion people live in our country in 36 states. And as I told you in the beginning, we are fast urbanizing. By 2050, 815 million people will live in urban areas. By 2030, it will be 59 crore people. The last census was conducted in 2011. That time we had 30 crore buildings, housing stock, out of which 60% of housing stock is permanent in nature, and is a cause of serious concern. Out of this 30 crore building, more than 50% buildings are masonry buildings. Okay, and you can see more than 50% area in the country falls under seismic zone 3, 4, 5, which is moderate to high seismic zone. 66% of our population and 63% of housing are located within these zones 3, 4, 5. Our mega cities, whether it is Mumbai, Kolkata, New Delhi, are amongst 20 largest urban agglomeration of the world, and thereby having higher risk. Okay. This you can see, if percentage wise, 50% area of our country is vulnerable to earthquakes, 18% of land is vulnerable to high wind velocity, and and we have a very high, coastal area is more than 3,000 kilometers, and every year we witness a whole lot of cyclones. So 8.5% area, primarily coastal area, is exposed to cyclones. 7% area is vulnerable to earthquakes, to floods, and hilly regions in 18 states is vulnerable to landslides. And if you see here, more than 1 million houses are damaged annually, in addition to human and other losses. The earthquakes which are of magnitude more than 8 are classified as great earthquakes, and India is seat to many, many great earthquakes, and I have listed them here for you. 1890. The only problem is now we are just waiting, because as I told you, the return period of earthquake is quite high, and God forbid if an event of this sort of if India is to face an earthquake of more than 8, this will be disaster. And there have been number of studies where it has been shown that if 1819 Kutch earthquake repeats now, the disasters will be, it will be, the losses will be of, enormous, which cannot be, even defined. So there will be so much loss and all. Okay, so you can see 1819 we had an earthquake of more than 8 in Kutch region, Assam 1897, 1905 in Himachal Pradesh, Kangra 1934, Bihar Nepal earthquake 1950, Assam Tibet earthquake 2005. There was earthquake, Kashmir earthquake, which came in Pakistan but caused losses in, like, just why I'm putting these pictures for you. Just imagine if this earthquake is to come again, and these are vulnerable areas. Bhuj earthquake in Kutch region, which came in Kutch region, that place had a history of earthquakes earlier, that 1819 earthquake, and despite of that, earthquake came there and we were caught napping. Again, there were huge losses of life and properties. Okay, and every now and then, whenever earthquake comes, as I told you, that we are a reactive society. We put in place repair, retrofitting measures. We come out with guidelines, codes, but after some time, because of implementation and other issues, and we wait for another earthquake to come, and when we witness that earthquake, the same story is repeated, which we saw during the previous event. Okay, and these are some of the great earthquakes, and recently, all of in the last 1990 to 2005, in fact, our urban areas, or tier 2, tier 3 cities had urban areas were struck with earthquakes. Like 1991 we had an earthquake in Uttarkashi, 1993 we had an earthquake in Latur, Jabalpur 1997, 1999 we had an earthquake in Chamoli. Then 2001 was an eye opener for all of us, because that earthquake came in Bhuj, and then Ahmedabad, which was 300 kilometers away from Bhuj. There, multi-story reinforced concrete buildings collapsed like a pack of cards, and thereby, everybody was in shock. Like, the properly designed buildings, how could they collapse, leading to huge loss of life and property. 2005 Jammu and Kashmir earthquake also, cause huge destruction and all. And then cyclone also, every year we have cyclones, floods, and 2004 tsunami also caused a whole lot of losses. So these are the major natural disasters. Just again, you can see average return period of earthquake more than of earthquake of magnitude more than 5 in our country is less than 2 months. Okay, and if we have to divide the entire region into these, Kashmir and Western Himalayas, Central Himalayas, Northeastern region, Indo-Gangetic Plain, Run of Kutch, Peninsular India, Andaman and Nicobar, you can see everywhere, all areas in our country are, prone to or susceptible to earthquakes, and anywhere earthquake can come. And if you can see Himalayas and all, earthquake of magnitude 8, there is a probability of 2.5 to 3 years, and earthquake of magnitude 5 to 6, there is a probability 25. Okay, no, 25 earthquakes is have occurred during that period. Okay, so there is an average return period of more than it. Now, just to give you some idea about the losses due to disasters: Kashmir earthquake, 95,000 deaths; Bhuj earthquake, 13,000. 18, and you see, same place, 1819 earthquake, Kutch earthquake came that time, deaths were only 1,500. So just think, because of fast urbanization, the kind of built environment we are constructing or developing, all these are becoming death trap, and will create, will amount to higher losses of life and property. Latur earthquake, Latur was in peninsular India, which was supposed to be seismically stable area. There also huge destruction, around 8,000, 7,928 deaths were reported, and majority of these deaths were in masonry buildings, and masonry buildings in our country are normally unreinforced and constructed by the artisans without seeking help of engineers and architects. And all these masonry buildings, as I told you, the last census, out of those 304 million buildings, more than 50% buildings are masonry buildings. And so these buildings are the cause of deaths during last previous earthquakes. In terms of, if you look at average number of deaths, you can see Latur, around 200 deaths per thousand; in Bhuj earthquake, 17 per thousand. Then, because Latur area was seismically stable, and there are no, all the roofs and all were quite heavy, and that is why there was large losses. And in terms of, if you look at in terms of, uh, money, 25,000 crore was the loss, around 5 billion US dollar. And similar earthquake, if it comes under Indo-Gangetic plains, it can be far more expensive. So as development takes place, concern moves from number of deaths to economic losses. So it's about deaths, economic losses, whole lot of things, happen because of earthquakes. This By this time, you are familiar. This was the earlier. So I've been telling you about earthquake. So how to estimate the earthquake hazard? So there is a Indian standard, which is IS 1893, which divides the entire country into seismic zones. So this was the map which was published in 2001, which 2001, what happened after Bhuj earthquake, the map was revised, and 5 zones were reduced to 4 zones. So seismic zone 2, seismic zone 5, comprising of, you can see, Bhuj area, then northeastern region and Kashmir area. Seismic zone 4, you can see this Himalayan region, part of Himalayan region, and Central India, then 3 is peninsular India, and 2 is this. So this was the hazard, earthquake seismic hazard map of the country. But now this map has been revised. We have come out with the recent one, IS 1893 2025 has been published just a month back, and I will show you that map as well. So now these 4 zones have been converted into 5 zones. We have included 2, 3, 4, 5, and 6 zone. Okay, so and there have been a lot of apprehension. So MSK is the intensity. Normally, this is the magnitude. Normally, earthquake is measured in terms of magnitude, and in our courts, we have simulated the earthquake hazard zone with the MSK intensity, which is a MSK is the scale, MSK scale. So if it is more than 9, then it is seismic zone 5. If it is 8, and their explanation is given in code. So if your area falls under seismic intensity 9, so there are two kinds: modified Mercalli intensity, and this is Medway Sprotonic scale. So if intensity is 9, then what will happen during earthquake? That can be found out. See, there will be falling of walls, there will be large cracks in the walls, there can be structural failures. All those things are given in the code, that if your area falls under seismic intensity this, then what will be the effect of that earthquake. So zone 5, 4, 3, and 2, they are related in terms of intensity. Okay, so this was the map which I think most of us know, and now this map is replaced by another map where we have again resorted to the 5 zones. Okay, and we have added another zone, 2, 3, 4, 5, 6, and all these zones are revised. I will just give you the brief history, that how these maps and things are evolved. So the first map came in 1962, then it was revised in 1966, and all our maps, that time India, we didn't have any instrumentation, other things. So based on whatever earthquakes have come, okay, so all the earthquakes which are reported in the country, based on that, the maps were created. The entire country was delineated into different seismic zones. So the major problem with these maps were that, suppose a place where the earthquakes are coming quite frequently, so that frequency was not incorporated. Only the earthquakes which have come, whether it is high intensity earthquake or low intensity earthquake, based on that, these maps were produced. But now the map which the recent map, we have tried to incorporate the frequency and other aspects as well. Okay, so that is the basic difference. So this is the first map, 1962. As you can see, there were zone 0, 1, 0, 1, 2, 3, 4, 3, 0, 1, 2, 3, 4, 5, 6. So there were 7 zones. As you can see on the left hand side, the map A. So this was the earliest map published by Bureau of Indian Standard, where the entire country was divided into 7 zones. And as you can see, white area is entire peninsular India, which was supposed to be seismically stable. And this map, as I told you, did not incorporate frequency and other geological features and all. It was based on earthquakes which have occurred in the country. And then later, and after that, this map was we kept on revising this map based on the earthquakes which were occurring in the country. And same thing happened when 2001 Bhuj earthquake came. We divided and again reduced the zones from 5 to 4. We just eliminated zone 1 and zone 2, 3, and 4 and 5. Then in 66, again based on the earthquakes, there were the map was revised, and again we had 7 zones in 1966. Then in 67, Koina earthquake came. So again, the map was revised, and 70 we had this map. So again, the entire country was divided into 5 zones: zone 1, 2, 3, 4, and 5. So this was the map which was used in 1979 Indian Standard. And then after that, 2001 Bhuj earthquake came, and the map was again revised. And this is the most familiar map, which all of you know. So this map again here, the zone 1 was completely omitted, and then we had only zone 2, 3, 4, 5. So the country was divided into 4 zones, and from 2002 to 2025 we have been using this map. But now, based on the current knowledge, based on advancement in knowledge, based on the data, and incorporating probabilistic, so earlier these maps were based on deterministic hazard. Deterministic hazard means the earthquake which have occurred in the country. But now the 2025 map is based on probabilistic seismic hazard analysis as well, and I will show you that map as well. So again, if I have to give you in tabular form, this is the thing, 1962. And as I told you, these hazard zones are, associated with the intensity level. And the explanation of this intensity level is given. Intensity means the likely damage uh, uh, because of this. So suppose you are in intensity 7 or intensity 8, what would be the likely damage to your structure or your area that is given? Okay, so these the moment you find this zone 3, you connected with the intensity, and you will be able to find the likely damages. So again, that is qualitative. Okay, so 62 we had 7 zones, 66 7 zones, they were reduced to 5 zones in 70, and then they were reduced to 4 zones in 2022. So you can see here MSK intensity 6, zone 1 and 2 were merged, then 3, and then 4, then 5. And now, as I told you earlier, that the now nationwide earthquake hazard map define expected ground motion intensity and ensure harmonized structural design across the country. These hazard maps can directly be used to do the structural design. And for that, what you have to do, you have to find out the likely ground motion multiplied with the mass, and you will get the lateral force, which you can apply in your building. So yeah, these maps, as I told you that earlier, the approach was rudimentary, based on deterministic earthquake hazard analysis, and now it has been based on probabilistic earthquake hazard analysis. Okay, so this is the map. Again, this the, map, you can see this is the latest map, and this was published in the Indian standard. Before getting it published, they put it in public domain for wide circulation. So this was the map which was circulated and was in public domain, and still people are using this map. But the BIS IS 893, which has finally been published now, there is slight difference between the map which was circulated and the map which is published. So that is why I'm showing you both the maps. So this is the map which is widely circulated. Zones and everything are same, but there is some change in the area. So please don't use this widely circulated, but use the map which is given in the finally published 1893. So this is the map. So you can see this is the map which you need to use. And as you can see here, again, India is divided into 5 zones. And intentionally we have kept zone 1 out. We are starting from zone 2. So we have zone 2, 3, 4, 5, and 6. And the areas which were falling in zone 2 earlier may fall in zone 3. The areas in zone 3 may fall in zone 4. Some zones are so, somewhere zones are enhanced, somewhere zones are kept same, somewhere some areas or some places the zones are enhanced by 2 times or 3 times. And there have been a lot of apprehension when this code was published that there will be rise enhancement in cost and all because of rise in lateral force. Yes, that is right. But this time the committee, the CD 39, was quite aware that safety is something which should not be compromised, and safety should be given top priority. And that is why, if you look at the attributes, safety is the first thing which need to be given importance. So if I have to give you, if you do any project or any structure you design or you construct, there are several attributes to it. One is safety, sustainability, functionality, then aesthetics, and then economics. So these are the 5 attributes, and the first and foremost attribute is safety. Then is then is functionality, then sustainability, and then aesthetics and economics. And aesthetics and economics you can interchange. uh, if you want more static structure, you can compromise with the cost. If you want less cost, then your structure can be less. But the first three are very important, and priority should be given to the safety. And that is why this time, realizing the safety to be given, because of huge losses of life, property, and as I showed you, economic losses, and it can create whole lot of other effects as well. Because of that, safety should be given due importance. And this map is based on probabilistic seismic hazard, incorporating other things also. And this time also, earlier codes have deterministic approach, and this time or prescriptive approach. This time we have incorporated performance based design. Performance based design means that it will depend the kind of structure you are designing. Suppose you are designing a nuclear power plant, or a dam, or a residential building, or a lifeline hospital. What should be its performance during earthquake? So based on that performance, you accordingly design the structure. Okay, so these are the 5 zones, and we have to use this map. And why this map is useful? Because this map will help you in estimating the earthquake hazard. And to estimate that earthquake hazard, you can find out the earthquake force your structure will be subjected to, and you have to design your structure for that later force. Uh, Estimating, finding out the earthquake zone, and then putting it, converting into the lateral force. So for key changes, again, there have been changes. So as I told you that now the previous 4 zones, 2, 3, 4, 5, are now demarcated into 5 zones: zone 2, 3, 4, 5, and 6. And just by demarcating, converting 4 zones to 5 zones, there have been shifting of boundary of zones, causing many towns and cities to fall in 1 to 2 level higher zones. Understand? Earlier zones were 2, 3, 4, 5. Now zones are 2 to 6. So again 5 zones, and because of shifting of boundaries of zones, many towns and cities now fall in 1 to 2 level higher zones than the previous. So that amounts to that your structure will be subjected to higher seismic forces. Like for example, cities like Bareilly, Patiala, which were earlier in zone 3, Almora, Chandigarh, Darjeeling, the Dehradun, Gangtok, Nainital, Shimla, which were previously in zone 4, they now fall in zone 5 and zone 6. Like Bareilly and Patiala, they are 2 zones above. So from zone 3 to they have come to zone 5. Similarly, Dehradun, Gangtok, all these highly seismic, vulnerable areas, they fall now in seismic zone 6. So added to this is the fact that estimate of peak ground acceleration has generally increased. So because of change in zone, and also because of incorporation of probabilistic seismic hazard, the peak ground acceleration has increased in each zone. Okay, so the design forces, again for design forces, earlier we were having importance factor and all, but this time importance factor has been capped 1. And we have kept the different return periods. So earlier, the return period was not there. Now, based on the kind of building you are designing, you can choose the return period, and based on the return period, you can estimate the earthquake force. So this is the major change. Now, based on return period, you will estimate the seismic hazard. Okay, like buildings which are of higher importance, they will be designed for higher. Suppose you are designing a critical building or a nuclear power plant, so that will be designed for 2475. If you are designing a smaller, normal residential building, then it is designed for the return period of 475. Okay. Also, earlier, we were giving load factors, design load combination, all those things have been changed. So I will just show you that what is the percentage increase in earthquake design forces. So just to compare, I think if you find it slightly complicated, so just see, this is the earlier formula which was given in 1893-2000. Z by 2, Z is the zone factor, which is zone 2, 3, 4, 5. I is the importance factor. R is the response reduction factor. That means if you're designing a reinforced concrete building, then response reduction factor will be 5. Masonry building, it may be 3. So that is that. And SAG is depending from the response spectrum. So the structure which you are going to design, you will find the frequency. I'll show you response spectrum also. Based on the response spectrum, you can find out the acceleration. So this will give you acceleration value. Then when it is multiplied by the weight of the building, you will get horizontal seismic coefficient. Okay, so and YL is the load factor. So load factor is some 1.5, 1.2, but this time we have removed that load factor. As I told you, we have removed the I is always 1. So zone factor, again based on zone 2, 3, 4, 5, that is your zone factor. Then this A is SA by G. So this time this multiplied by weight will give you the seismic coefficient. Okay, so earlier, if you see zone 2, 3, 4, 5, zone factors were point. So this is Z. So this is 0.10, 0.16, 0.24, 0.36. And now, as I told you, now we have introduced the return period. Okay, so return period 75 to 9975, and based on the kind of type of structure you are designing, you can pick the zone factor from here. Okay. Okay, so now let me also tell you about the percentage increase in design earthquake force coefficient. The zone factors which were given in 2016. So if I have to compare these zone factors, so we are assuming that G zone factors were based on return period of 2475. So the 0.10 is converted into 0.15, 0.16 is converted into 0.25, 0.24, 0.35, 0.36 to zone 4 is 0.35, 0.24, and zone 5 is 0.5, and zone 6 is 0.75. Okay. So, and again, as I told you, the response reduction factor is kept, but importance factor is now 1. Earlier, depending upon the kind of building you have, like crucial services, you have a response reduction factor. This importance factor 1.5, for important buildings 1.2, and all normal buildings it was 1. But this time we have kept I1, but we have changed the return period. So based on return period, you can have the zone. Yeah. Okay. And now let me just show you this also. I will. Yeah. So you can see here normal building, important buildings, and critical buildings. So what should be the percentage increase? Suppose you are in zone 5, then for normal buildings, there will be percentage increase of 23%. The forces will be increased. Important buildings also 23, critical buildings 23%. Then if it is in zone 6, earlier that zone was not there, so there is an increase of almost 100%. So again, this is the comparison just to show you that there is considerable increase in the seismic lateral force. Okay, and again, I have been repeatedly telling you that this time safety is given top priority, that it should not be compromised. Okay, so you can see for normal building, revised current percentage is nothing. Zone 3, 4%, zone 4, 29%, zone 5, 23%. Similarly, important buildings 11, 16, 30. Okay. So this was for where we have the same zones. Suppose the earlier published code and now published code, the zone is same. Then this is the increase. But if your zone is enhanced by 1 level, then this percentage increase is quite high. It goes up to more than 100% even for critical buildings, or 86% for important buildings. Okay, and if the seismic zone is 2 level higher, then this goes by more than 200%. So I thought of showing you this data, and this is again this is something which we have National Disaster Management Authority, they created expert group, and they created an expert group comprising of the IIT Madras, IIT Bombay, Central Building Research Institute, and then IIT Roorkee, and other academicians, and created created a group and asked them to submit the seismic risk assessment of the country, and they submitted a report to NDMA, and all these things which I showed you, all these tables, all these maps are part of that report which is submitted. So this is an authentic data taken from that report. And since there have been a whole lot of apprehensions amongst professionals that there will be considerable substantial increase in the force and all those things, so that is why objectively we have put these things in the report. And yes, there will be increase, and so we have to choose between safety and other aspects. So this time safety is given the priority. Okay, so this anyway I will not cover this anyway. There have been other key concerns also regarding region specific attenuation, and so I'm not going into detail of all these things. Then this time soil, effect of soil, if your building is founded on a rock, or if it is founded on an alluvial plain or on a marshy land, the effect of earthquake will be different. There will the earthquake waves gets amplified when they pass through soft soil, and if they pass through hard soil. If your building is founded on rock, nothing may happen, so the seismic waves may get attenuated. Okay, so that thing has also been taken into consideration. Earlier also it was taken into consideration, but this time it has been taken through this response spectra which is given. So if I have to show you, so the entire country is divided into these site class. And earlier also we had this were based on n values, SVT values, and this time it is based on shear wave velocity. So these are the site class. Okay, share based on so there are five soil conditions, and based on that you can choose the response spectra, and from this response spectra you can find out the this, horizontal acceleration. Okay, so this just to make you understand, this is the seismic zoning map. So from this seismic zoning map, this is the formula. See, from seismic zoning map, you try to find out this coefficient. I, R, and everything is given in tabular form. Then you have to find out this A and H, and W is the weight. So for this A and H, what you will do? So Z is from this table, where you choose the what kind of building you are creating. Based on that you will choose the return period, and based on this return period, in which zone your area is falling, you will choose the jet factor. So you will take just jet factor. Then for A and H, what is the seismic coefficient, you will use this response spectra. Okay, and this response spectra, you have to find out the time period. And for time period, again, this is a natural period for which detailed formulas are given in the code. So based on that, depending upon the height of your building, width of your building, type of building, you can estimate the time period readily. And once you know the time period, you will depending upon that time period, you can find out the design horizontal acceleration. So that acceleration, when multiplied with the weight, will give you the horizontal force your building will be subjected to. And again, uh, here we are incorporating the soil conditions. So this is in all about the IS 1893, and very soon there will be few explanatory handbooks will be published by BIS to make the things easy so that everyone can comprehend this. So this was all about 1893, and I thought I will try to address some of the apprehensions of the professionals about these codes. Okay, so now let me move to the easier part. As I told you that every now and then, whenever earthquake comes in the country, we come out with the robust codes, we come out with guidelines and all. But over the years, we keep on forgetting about this. So in 1935, when India was not even uh, independent. That time earthquake came in Quetta, which is in Pakistan, and that time there was huge loss of life and property during Quetta earthquake. But in Quetta there was military establishment, and they came out with the code that time in 1935. Okay, so there they introduced lintel band, corner reinforcement, and all these things for masonry buildings, and the entire Quetta town was reconstructed. Okay, and then again earthquake came there, and the buildings which incorporated those earthquake arresting measures, they performed very well. So that time that bond was called Quetta bond. Okay, and but after some time we forgot, because that was the military installation, so they could enforce those earthquake resting measures. But with the passage of time, all those things were forgotten. And okay, and this is, as I've been telling you, that loss of traditional architecture and knowledge. Earlier development, you see the Diwari in J&K, where they put this kind of stiffeners, this kind of braces and all, braces in masonry buildings, thereby making it more resilient during earthquakes. So that time, in 19th century, these kind of construction were, which were quite good with regard to earthquakes. But nowadays, these are being replaced by simple unreinforced masonry, which is quite detrimental as far as earthquake is concerned. Okay, Assam type house, all of we have Ikra walling, and then we have bamboo, which is excellent for seismic resistance, lightweight roofs, all these traditional structures. Okay, and this already I told you that that was known as quetta bund, which now we have lintel band, plinth band, and all those things. So that time in 1935, the first seismic code was developed. In fact, that time 10%, point 0.1 was the seismic coefficient. That time, after 1935 earthquake, the code was formulated, and it was said that all the buildings should be designed for 10% of their, the horizontal force should be 10% of their uh, weight. Okay, so 1935, all these things were given. You can see quota bond, vertical reinforcement, corner reinforcement, everything was given during that earthquake. Okay, so but with time we forget that. Now let me just tell you that it's not now. The 2001 earthquake was the eye opener for all of us, and that is why after that, government, earlier disaster management was the part and parcel of agriculture ministry, and then it came under Ministry of Home Affairs. Then NDMA was established, National Disaster Management Policy came into place, Disaster Management Act came, building bylaws came into force, a whole lot of things came, because there was huge, all kinds of buildings, properly well built, reinforced structures, reinforced concrete buildings, high rise, posh apartments in Ahmedabad. They collapsed like pack of cards. So I'll just show you. So you can see these are masonry buildings. Masonry buildings, because they are normally unreinforced buildings, so they face the major brunt of any event. And you can see whole kind of buildings you will find. Railway stations, schools, some other buildings, panchayat gas, all kinds of masonry buildings made of stones, made of mud, made of bricks. All of them suffered huge losses and caused huge loss of lives as well. You can see in this thing. Okay, then these are, as I told you, that again, another important thing which was observed during the Bhuj earthquake was soft story. So the buildings which are on stilt, normally the ground story is left without walls, to give space for parking. Mm. And so these buildings are called soft story buildings on a stilt. So all those buildings, were quite detrimental to the earthquakes, and it was observed that soft stories are much, much, much more vulnerable than the normal buildings. And after that Bhuj earthquake, we incorporated in Indian standard. If your building is soft story, then you have to design it in a different way. You have to design it for much higher forces. Okay, so you can see a whole lot of buildings where nothing happened to the building, but the ground story collapsed because it was a soft story, because there were no walls into it. Okay, so you can see your whole, all kinds of buildings, staircases. There were huge losses of staircases, collapse of staircases, people running through staircases, and those staircases collapsed, leading to a loss of lives. And then the clauses on staircases were also changed in Indian standards. Okay, then there was again a whole lot of work was done, and heritage structures, more than 10,000 heritage structures suffered huge damages, domes and all of historical buildings, huge walls, stone masonry walls, they all collapsed during the earthquake. So heritage buildings also suffered damage during the earthquake. Then there is another important thing which came into which we observed that after immediately after earthquake, everybody resort to repairing of structure. So, but it was found that repair, most of the time this repair is cosmetic repair. We just without getting into the how the structure failed and how it should be strengthened. So strengthening is strength. We need to understand the difference between strengthening and repair. Repair is something cosmetic. If something is falling, you just put some support to it, and make their structure again. But if an earthquake comes again, you are not strengthening it for horizontal load or for ground shaking. For that, you have to seek an advice of a structural engineer, and you have to understand the building, its structural type, the damage and other its strength, residual strength, all those things. It's a very scientific and expert area, and you need to seek advice of experts for doing retrofitting of structure. So just looking at the damage and just covering it with the plaster and putting some sort of support without connecting it with the other parts of the structure will make your structure more vulnerable or more detrimental to the future events. So unscientific retrofitting is to be prohibited, and you have to have specialized contractors, specialized professionals need to be consulted for undertaking any repair, any strengthening or retrofitting work. So repair is cosmetic, retrofitting is strengthening of your building scientifically. Some of the failures I'll just show you quickly. So you can see here, this is a heavy roof which was just put on steel tubes, and that is why the entire roof failed. You can see here again, same thing. You can see this is random rubble masonry, and so there's a thick wall. And what you see here, that wooden thing is, just because of this, the upper story did not fall. So this is we provide a lintel or lintel band. That is the beauty of lintel band. Lintel band connects all the walls together, thereby making your building safe. This is again out of plane failure because thick wall, and because that thick wall gave away during earthquakes. You can see this is a classical example that this forward because of this wooden plank which acts as a lintel, the upper story was safe. Yeah, again the same picture you can see. So you can see because of this band, nothing happened to this building. So if you provide a reinforced concrete beam, which is called a lintel band, at the opening level, at the door or window level, lintel level, then your building will become. This is that soft story I was talking about. You can see the entire building. There was a soft story. So the entire ground story is collapsed, and nothing happened here. You can see. So this was observed during Bhuj earthquake only, and after that, soft story concept was put into the code. You can see this. This is out of plane failure, where this the longer wall, failed. This is a staircase collapse. You can see these two buildings were connected together, and this gave away. Here, this what you see, this is the intermediate story collapse. So here, the classical thing was this building was initially, constructed for some purpose, and later on, this story was converted into a gymnasium. So they removed some of the walls and created a created a to create more space. That some walls and other things were replaced, were removed, and a gym was created. So that was fine for vertical loads, but for horizontal loads during that earthquake, this nothing happened here and here. But this intermediate story, because of later changing the building later, this intermediate story collapsed. Okay, so this was just wanted to show you, and now I'll quickly show you pictorially some measures for earthquake resisting measures and planning and design measures to you. Okay, so again, after 2001 earthquake, IIT Roorkee Department of Earthquake Engineering, they published some of the handbooks or in pictorial form, so that masses at large understand the earthquake and related phenomena better. I have taken these pictures from those guidebooks, where, in a very simple pictorial form, the complicated earthquake things are being explained. Okay, so first of all, let me again clarify this, that we don't say that building will not suffer damage during earthquake, because you cannot design any building which will have no damage, because we don't know what kind of earthquake will come and what would be the intensity or magnitude of that earthquake. So the philosophy of earthquake is that during minor shaking, there should be some damage. During moderate shaking, there may be some collapse of wall, and during strong shaking, there may be collapse, but there should not be any uh, life-threatening collapse. Understand? So during minor shaking, there should not be any crack. Moderate shaking, there should be some cracks and all. And during extreme strong shaking, there may be, there will be, the building may suffer damage, but it should not collapse. So collapse prevention under strong shaking. So that is the philosophy. Philosophy is there should not be any life-threatening collapse to your building. So that is why earthquake design is special, because here we are allowing damage to occur in building. We are not making building which will not have any damage during earthquake. We design buildings so that it has damages which we decide. Okay, so building should fail in predetermined manner. So building should, that is why the earthquake design is challenging. We are allowing damage to occur, but that damage should occur in predetermined fashion or predetermined manner, the way I want. That damage should not lead to collapse. The damage or building should fail, but there should not be any life-threatening collapse. So that is the philosophy. Okay, and that is why this performance objective is written. Minor shaking, there should be low repairable damage under minor shaking, and there should be collapse prevention under strong shaking. And you can see, so the basic philosophy is to ensure continuity to vital services, to prevent human injury and loss, and to minimize damage to property. Okay. So now, again, these are self-explanatory, so I'll go slightly faster. The building should be sufficiently away. You can see here, so building should be sufficiently away from a steep slope, because during earthquake, the steep slope may fail and thereby endangering your building. Similarly, if you have a filled-up soil, you should not, create a foundation of your building on a filled-up soil. If you have a filled-up soil, you have to go for pile foundation or something like raft foundation, and take your building. The building should rest. Your foundation should rest on a hard strata. Okay. Similarly, these kind of structures, asymmetry should be avoided, like T, L, U, X plan. All these kind of plans should be avoided. And if these plans are mandatory, then what you can do, you can divide this into four parts, three parts, like this, three parts. So you provide a separation joint. The plan will remain the same, but only thing is, when you have this kind of thing, there will be severe cracks and all damage at these corners. But the moment you separate these and create in three blocks, there will not be any, because all these three blocks will behave independently during horizontal shaking. Okay, so you can create a separation joint. So these asymmetric buildings, so simple symmetric buildings is the key for earthquake resistant construction. So asymmetric buildings undergo torsion, and extreme corners of the building are subjected to very large earthquake forces. Similarly, again, you can see here, too long, too tall, too large in plan buildings need to be avoided. So suppose you want just too long buildings. So what you have to do, you have to divide it into number of pieces, 2 or 3 pieces. Similarly, too tall building is to be avoided. Similarly, you can say simple plan shape buildings do well during earthquakes. Okay, so you can see simple plan square rectangular buildings will have better earthquake performance. Otherwise, you have to provide separation joints. Okay, again, you can see this general shape, inverted pendulum. This should be avoided. Building should be this kind. Very slender building should also be avoided. So the thumb rule is H/B ratio should be less than 4. Similarly, this kind of building where you have a top like this is to be avoided. This kind of thing should also be avoided, because it's not symmetric. And here, this huge mass is acting on this. This is to be avoided. And if you want this kind of building, you have to create into 3 parts, or here it should be in two parts. Similarly, large kind of, during Jabalpur earthquake, parapet wall or the balconies, they suffered a whole lot of damage. And sometimes balcony, if you're coming out of your building during earthquake and balcony, a brick falls from the balcony, that led to the loss of a life during, Jabalpur earthquake. People were coming out of a three-story building, and a brick fell from the parapet, causing a loss of a military person. So avoid large balcony, avoid this kind of things. Then this is something, again, another thing is called floating columns. In normally municipalities count the ground coverage area. So to have the better FAR, they provide less columns in the ground, and more columns in the, so the columns coming from top story to the first floor are terminated at the first floor, so that they get advantage of better FAR, because FAR is based on the ground coverage. So this kind of floating columns, again, it was seen during Bhuj earthquake. The floating columns are very dangerous because there is no clear load path for your the building, because this column is terminated here. Ideally speaking, this column should go here, or otherwise there should be proper mechanism for transfer of load. Okay, so these things to be avoided. Large projection should be avoided. Similarly, if the buildings are, these kind of buildings, suppose there is one buildings of two different heights. So during earthquake, what will happen? This building will, hammer this building here, and thereby causing damage to this building. So there should be a separation between two buildings. And again, code, there are, gaps. What should be the minimum gap per story is given in IS. There is Indian standard 4326, which provides that gap. So 20 millimeter per story gap is given for buildings. Then separation joint, again, as I told you, that if you have to create dissimilar buildings or asymmetric building, you have to construct that building in different parts, and in between you have to provide a separation joint. So again, separation joint should not be stiff, because it should allow the movement to take place. Because during horizontal shaking, during the ground motion, there two buildings will strike to each other. So if you provide a separation joint, that separation joint should have a softer material, like some kind of rubber kind of thing, and then it should be properly. So separation joint details are again given. So it should be bitumen filler, so that it allow movement to take place. Okay, so there should be compression in that, so that material should be flexible enough to allow movement to take place. Okay. Then see, again, as I've been telling you, that non-engineered construction is something which suffer damage, which suffer most of the damage, and thereby there are guidelines published for non-engineered construction also, some thumb rule kind of thing. So the minimum depth of foundation, like, should be more than 150. If you are having a foundation of soft soil, then it should be more than 500 mm. So all those kind of thumb rules are being given. Then if you have a liquid, see, if your building is on a marshy land or on a softer soil, then you need to provide the piles like this. Okay, and it has been found during earthquake that if you have a alluvial soil or a softer soil, so soil behaves like a liquid. So it is called, so soil gets liquefied. Okay, because it is an alluvial soil also, because during shaking, and if water table is high, soil will become like a liquid, and the entire building may sink. So liquefiable soil, you have to provide the pile. Okay, now sloping roofs, so this is called gable, and if you go to villages and all during earthquakes, this gable, and because if you don't create a gable band here, so these walls will fall during earthquake, and the moment this wall falls, the entire structure, the entire roof will get dislocated, leading to loss of life. So pitched roofs, normally the hip roofs are better, because you can provide this kind of band here. This long wall and this wall will behave separately. Okay, and thereby most of the gable ends, they suffer lot of damage during earthquakes. Okay, so hip roofs are better. You can see here. And if you want to make a roof, so that you have to properly connect it with the, cross bracings and all. So give like this, so that the idea is that the entire roof structure, the entire building should act together. So you have to connect all the parts together, okay, so that building behaves together during shaking. Okay, and as I've been telling you that again during Bhuj earthquake, it was found that staircases collapse. So you have to separate the staircase part with the main building. So what happens? You can see here. This is a staircase. If it is the part of the structure, then during earthquake, during shaking, this will act as a bracing. And once it acts as a bracing, this column or wall will behave differently than it was designed. So it is better to separate the staircase with the main structure, so that during earthquake, staircase behaves separately and this behave separately. Okay, so again guidelines are given in code. So to avoid bracing or strut action, the staircase should be separated from rest of buildings. So detailed guidelines are given. You can see this. Okay, so this is your these are your columns. So you have to create a separation joint, and you have to create a separate structure for your staircase. Fine, I'm not going into detail. You can see here. So yeah, here it is shown better. So if you create like this, so this will act as a strut or bracing, and thereby endangering this structure. So what you do, you just create a small gap. So you have created a separate staircase and a separate building. Okay, and you provide a separation gap here. Building will remain same. Only thing is you are allowing movement to take place here. Okay, so earthquake resistant detailing is required for staircases and must be carefully designed and constructed. I gave you the example of parapet wall. So parapet wall you can always create, but that parapet wall or any attachment, whether it is balcony or supported ceiling, they should be properly secured with the main structure. Parapet wall is something very important. So parapet wall, you want to create a parapet wall, so you have to put a reinforcement in a parapet wall and connect it with the reinforcement of your roof. Okay, so that parapet wall acts with the as a part of the building. Okay, then again large overhang. Again, it was during, you might have heard that during Bhuj earthquake, a very posh apartment, very high rise structure, it collapsed, and later it was found that the residents of that building wanted to have a swimming pool in rooftop swimming pool. So they created a rooftop swimming pool. And once you create a rooftop swimming pool, whole lot of water and that water was not taken into account during the design. So that was later addition, and because of that heavy mass at the top, the building collapsed. So these, you might have seen very recently, earthquake came in Philippines, and there was a in TV there was a report where the building was shaking and whole lot of water was spilling out at the bottom. Okay, so swimming pools or any heavy structure at the top should be avoided, and if it is inevitable, then you have to properly connect, giving it a proper load path, so that during earthquake the load is transferred properly. Okay, so this was about the planning, and now let me show you something about the masonry buildings. So as I told you that any normally masonry buildings are not designed in our country. So normally we have 9-inch wall, and then there are thumb rules that you provide 4.5-inch slab, then openings as per your convenience are being provided. So there is a code one, IS 4326, which in detail gives the guidelines that how to construct earthquake resistant masonry buildings. And India is the country where we have not only code on the brick masonry, but we also have a code on low strength masonry, mud building, stone masonry buildings. We have wooden buildings. For all these kind of low strength masonry buildings, we have Indian standard, and you can always make use of that standard to create earthquake resistant masonry building. Okay, so what is to be done? You have to first find out the earthquake zone, ground slope, soil type, building bylaws and surroundings, then select the shape of the building, then do the foundation design. As I told you, foundation design is also Very important. If it is a soft soil, then properly you have to design, you have to give the proper depth. If there is water table as high, then you have to go for pile. So all those kind of things are to be seen. Then wall design, again we normally take 9 inches as a wall thickness, but wall thickness, what should be the mortar composition, all those things again given in code, I will show you. And then wherever you have opening, you have to provide earthquake bands, and those earthquake bands are to be provided at any opening, at a plinth level, at a lintel level, and if at a roof level. And if your roof is of RC, then roof band is not to be provided. Okay, so I'll show you it pictorially. So this is what happens during earthquakes. These you should normally the structure is like this. So these are 4 walls, and now think. I always give the philosophy that earthquake philosophy is united we stand, divided we fall. So, and there should be a box like action during earthquake. So just imagine if this building, there is no connection between this wall and this wall. So during earthquake, what will happen? The walls will go separate. This wall will go like this wall will go like this. So you can see here, wall B is going like this and wall B A is going like this. Thereby there will be a separation here. So what you can do, you can connect all these 4 walls together through a band here or through a beam. So the entire structure will act like a box, and it will sway like this or like this. So you're not allowing any movement here. These 2 walls should act together. So box-like action is something which we need to achieve during for earthquake resistance. Okay, so how you can achieve that? By connecting these 2 walls together. So what we do, we provide a band. I will show you next picture. So you see here, so this will go like this will go like this, and thereby creating a separation here. So you have to create all the words together. So have a box like action to avoid failure. Okay, so that was for masonry building. And similarly, you can see slender walls. You can see here. So slender wall, very thin and long walls need to be avoided. Otherwise, what will happen? They may collapse. So again, in code, height by thickness ratio and length by thickness ratio. So length and thickness and h by and height and thickness ratio should be within limits. That is again given in code. Okay, so like you can see here, if it is a so long walls are to be avoided, and if you can't avoid this wall, if you require it for some purpose, then what you have to do, you have to provide a buttress of this kind. Otherwise, the best thing is create, instead of the single room, you can create 2 rooms by cross wall. But if you require this, then you have to put some kind of strengthening measure that is called buttress in a brick masonry, so that you can have a long wall, but so this long wall is avoided. Okay, so again given in code, unreinforced masonry wall length should not exceed 5,000, should not be more than 5 meters. So as I told you that this is the again given in code that minimum thickness of your foundation should be 500 meters. Then you have to provide a plinth band, and if you are going for RCC foundation, then this is the kind of foundation. Then plinth pile foundation if you have a marshy land. Then villages and all, we have random rubble masonry, ashlar masonry, or stone masonry. So as I told you that for stone masonry, you have to connect these 2 walls together. You might have seen in some heritage structures these kind of thing. Okay, so these are called thorough stones. So you provide this stone like this stone like this stone like this, so that there is a connection between these two at the corner between 2 walls. So during earthquake, both the walls will act together, because we have connected these 2 walls through these cornerstone, or these are called thorough stone. And similarly, when you have a very thick wall, so what happens, you just put these stones there, so it acts, these two acts differently, and thereby there will be a splitting here. So what you do, every 150 meters, every 1.5 meters, you provide a thorough stone, so that you connect 2 leaves. I think I have a second slide where I will show. So to avoid splitting of rubble masonry walls, you have to provide thorough stones. You can see here. So these are random wall masonry. So during earthquake, these will act separately. Thereby, there will be separation or bulging of wall. You can see here. This is a bulging of wall. So what is to be done? You can see here. So again, given in code, you provide, so every 60 centimeter, means 2 feet, you provide a thorough stone. So by just providing this thorough stone, what you are doing, you are not allowing this and this to act separately. So you can see in plan, this is how it is being provided. So every 1.2 meters, this in plan, and in height it is around 2 feet. Okay, and you provide this can be a thorough stone, it can be a wooden plank, and then you provide a small reinforcement also of this kind to connect these two together. Okay, so this will thorough stones or bond stones will be vital in preventing the wall from separating into two widths. Okay. Okay, then the openings, always opening, where should be the opening? Opening should be in the center. Okay, so again, code gives that what should be the opening. Normally, the opening at the corner should be avoided. Okay, the opening should be small as possible, and and it should be provided away from the corner. So it should be normally at the center. So this is given in code that minimum distance between your opening and the corner should be around 600 mm. Okay, and then you can see this kind of thing. Okay, so openings, where to provide openings, how many openings are to be provided. Opening should be less, because openings do, openings will weaken the masonry. So if you are providing openings, then you have to provide the reinforcement, a steel bar here, rebar here, rebar here, and then a band here. I'll show you next slide. Okay, you can see here. So this is what I was talking about. Bands you have to provide. So this is a plinth level. You have a foundation, then plinth level you have to provide a plinth band. Then at a lintel level you have to provide a lintel band, and at a roof you have to provide a roof band. So these bands, all these bands together will allow your building to act together, or will ensure box-like action between walls. So the entire structure, because these are connected, all the walls are connected together at different levels, will allow the box-like action. And similarly, wherever you have openings, you have to provide this corner and vertical reinforcement. So this kind of grid is being provided so that the building acts together. Okay, so this is how the band is being provided. This is called lintel band.
Shailesh
Yes,
sir.
yes,
Yes, sorry
yes,
for interrupting you.
yes.
Sir, would it be possible, sir, to finish it in 5 minutes because we are having next session?
Acha, okay. So I'll just take, I'll stop. I'm just few more slides, okay? So
Yeah,
just give
sorry,
me
sir.
5 minutes. No
Yeah.
issues, no issues. Okay. So this is the band, this is that band I was talking about. So I'll stop at masonry buildings only. So this is the band. When you have a random over masonry, and also you can provide a wooden plank of this kind. So idea is to connect all the walls together. And when you have the brick masonry, then you can provide this kind of, again, all these things are given in code. I'll show you some tables also. Then this is the vertical reinforcement which you need to provide. Okay, so this is how this band, and this is the typical band details, again given in code. So if the band depth is 75 to 150 if it is 6 inches, then you have to provide reinforcement like this, otherwise like this. And then corner detailing is also very important. You have to provide, at the corner, the detailing should be like this. The reinforcement should not be terminated at the corner. It should pass through in a continuous way at the corner. Okay, so again, this is given from the code we have taken. So suppose you are having a masonry building in zone 2, then what should be the mortar mix, what bands you have to provide it, whether you have to provide vertical reinforcement, what should be the dia, what should be the mortar mix, all those things you can take from this table. And if your building is on hard soil or medium soil, so just referring this table, you can find out what are the earthquake resisting measures. Suppose you are in zone 4, and you are constructing a building of 4 story. Then this should be the 1:6 should be the mortar for for brick, for walls. Then you have to provide a band at lintel, and at the roof and at the plinth. Vertical reinforcement you have to provide, which should be of 12 Then for vertical reinforcement, what should be the mortar mix, you have to, all these things are given. And again, if it is on soft soil, then what should be the earthquake resisting measures, that is also given. And the band, that band we are talking about, lintel band, roof band, and plinth band, what should be the reinforcement, what should be the thickness. Again, so zone 4, so suppose you are in zone 4, it is hard soil, then this should be the detail of your plinth band or your all the bands. So it should be 3 inches. The reinforcement should be 2 bars of 8 mm dia, TMT bars, and then this is the stirrup or link. Okay. So I think that is all. These are the Indian standard, as I have been told. Now we are revising all these standards, and you can all. Somebody was asking, you can download. You can go to now. The good thing is that BIS is now open. Earlier we have to buy the standards, but all these standards now, you can all these standards you can download by going to the BIS site. You go to BIS site, you register yourself, and then download all these standards. So these are these, as I've been telling you, that India is one of the few countries which have very exhaustive standards covering all kinds of buildings with regard to earthquake resistant construction. In fact, not only earthquake, but about floods, about cyclones, for landslides, for all these things we have standards and guidelines published by NDMA. So these are for earthquakes 4326, 13827, 13828, 13920, for detailing of reinforced, then masonry buildings 13935, for strengthening 15988 for seismic evaluation. So all these codes you should refer, and my advice or to you, or request to you, would be that if you are designing or constructing a building in earthquake prone zone or any disaster prone zone, please refer these codes and follow them religiously. Okay, so that's all. Because of paucity of time, I am not able to cover these things. In case you have any questions, you can write to me. I will, anyway, I will give this lecture to Sushant so that you can. So this was about masonry buildings. Then I wanted to cover something on strengthening, so that also I'm not covering. Then I this I'm not. Okay, I will just go to the last uh, 1 2 slide. I will show you. Yeah. So, the BMTPC, because earlier I was heading BMTPC, I recently retired in November. We have created a beautiful document called Vulnerability Atlas of India. So you can just, we have created a website for Vulnerability Atlas of India. So just by on a click of a mouse, you can just find out the hazard of your area. So hazard in terms of earthquake, hazard in terms of flood, hazard in terms of wind and cyclone and thunderstorm. So we have digitized map. You can just get an access to all these maps by visiting our website and get. So I'll just show you once. I'll show you this. Yeah. So these are the maps. I will just yeah. So this is the maps which are given. You can see. This is the earthquake map. Earthquake hazard map is given. Then wind and cyclone map is given. Then cyclone map, flood proneness. Then landslide incidence map is given. Then thunderstorm incidence map is given. And then we have district-wise tables are also given. I will show you another one. So this is a district-wise table where, depending upon the kind of house you are living, you can find out the vulnerability or earthquake damage risk. That if you are in zone 5 and if you are living in a masonry building, what should be the damage risk? And suppose it is in very high risk zone, then very high risk zone means that your building is likely to have some damage during earthquakes. Okay. You can note down this website. This is the website for that Vulnerability Atlas of India, vai.bmtc.org. And we are also running a course, e-vulnerability course, in association with SPA. So all of you can register for this course. There is a nominal fee of 500 rupees, and it is a self-learning course. And during the course, you can learn yourself about the various aspects which I just covered. You can download a whole lot of literature also, and once you finish the course, you can take up the exam, and you can assess yourself, and if you pass that exam, you will be given a certificate which is self-generated. So thank you very much for giving me time. I'm sorry if I've encroached in some other times. Thank you, Sushant, and I don't think, if you want me to take some questions, I can take. Otherwise, thank you very much.
Thank you, sir. Thank you, sir, for your wonderful presentation. And also, you have given a detailed insight about the retrofitting and strengthenings and also the codal provisions. Sir, with your permission, we can take a few questions and
Okay.
then we may wind up the session. Yeah. Sir,
Okay.
one of the parties was being asked,
Yeah.
uh, com-
Your voice is breaking, Sushant.
Sir, one of the questions, sir,
Huh,
has been asked: do
huh.
we need shear wave velocity as a compulsory requirement for calculating earthquake force as per new code?
No, 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 no. Share wave. See, earlier it was based on n value. So if you have n value, there are formulas given in code which will relate n with shear wave velocity. Okay. So there are empirical formulas also given in code. So depending upon the soil type, you can find out you can take the response spectra. Not an issue.
Okay,
Next.
sir. Sir,
Huh.
one of the question is asked like, why is zone one eliminated as the seismic maps are updated one? That's what.
That is intentional. So, if you put zone one, that means, see, again, in India, you have to constantly hammer the minds of the people. So earlier we had zone one. So zone one means no earthquakes. And now we say there is no place in India where we cannot have an earthquake. So we have intentionally removed, so there is no concept of zone one like earlier we had zone zero to zone six. So zone one means completely eliminated. Means there has to be some kind of earthquake thing. So that is why zone one is intentionally removed. Again, if we start with zone one to zone four, people will think that zone one means no earthquake. So it was very intentional by the government, by the policymakers, by the professionals that if we continue to zone one, so you may, being academician, you may take it right that zone one means what, but most of the people they will think zone one means it was no earthquake. So that is why zone one. So it's just a normal playing with the numbers. Okay, zone two is less seismic zone. Zone six is the highest seismic zone, but zone one is just removed to make everyone understand that there is nothing like no earthquake zone. Okay.
Okay, sir. Maybe we have also, maybe if the participant is having the couple of questions, they may send it to me and I'll
Huh,
compile all those and
huh,
give them
huh,
back.
huh.
Yes.
Okay.
Yes, sir.
Okay.
Thank you. Thank you,
Okay.
sir,
Thank you.
for accepting our invitation and for the sparing your time, sir. Would like to present you a small token
Okay.
of thanks from our side.
Okay.
Please
Okay.
accept
Thank
it,
you.
sir.
Thank you. Thank you very much. Thank you very much.